The energy density of a lithium-ion cell is directly tied to its cathode chemistry, primarily nickel-manganese-cobalt or nickel-cobalt-aluminum. Recycling must recover these high-value transition metals and lithium while minimizing energy input. Current global recycling capacity only handles about 5% of end-of-life batteries, creating a critical supply chain bottleneck for electric vehicle adoption. The challenge is separating the complex layered oxide structures, such as NNC 811, where nickel content is 8 times that of cobalt. The black mass, a mixture of cathode and anode materials, electrolyte salts, and binder, is the primary feedstock for chemical recovery processes. Efficient recycling requires breaking the strong chemical bonds within the cathode material, which are designed for stability during thousands of charge cycles. Before chemical processing, batteries require mandatory deep discharge to mitigate thermal runaway risk, which occurs when internal short circuits generate excessive heat, exceeding 1,000 degrees Celsius. The electrolyte, typically lithium hexafluorophosphate, dissolved in organic carbonates, is highly flammable and toxic. Mechanical shredding, performed under inert atmosphere like nitrogen, separates the casing and current collectors from the active materials. The resulting black mass consists of pulverized cathode materials, graphite from the anode, and residual binder like polyvinylidene fluoride. This black mass contains the target metals, cobalt, nickel, manganese, and lithium, alongside copper and aluminum foil fragments. The efficiency of subsequent hydrometallurgical steps depends heavily on the purity and particle size distribution achieved during this mechanical separation.
Pyrometallurgy, or smelting, is the oldest recycling method, treating batteries as a complex ore. The process involves heating the black mass to temperatures exceeding 1400 degrees Celsius in an electric arc furnace. During smelting, organic components, including the electrolyte and carbon, are combusted, providing process heat. Cobalt, nickel, and copper are reduced and form a metallic alloy, which is then refined. However, lithium, aluminum, and manganese are oxidized and partition into the slag phase, making their recovery difficult and energy-intensive. The high energy demand and the loss of valuable lithium, which is increasingly critical for battery production, are the primary drawbacks of this approach. Pyrometallurgy effectively destroys the cathode crystal structure, requiring complete resynthesis of new cathode precursors. Hydrometallurgy uses aqueous solutions to selectively dissolve target metals from the black mass. This approach operates at significantly lower temperatures, typically below 100 degrees Celsius, reducing energy consumption compared to smelting. The first step is leaching, where strong inorganic acids, such as sulfuric acid or hydrochloric acid, are used to break down the metal oxides. The overall reaction converts the solid metal oxides into soluble metal sulfates or chlorides. Hydrometallurgy offers higher recovery rates for lithium and manganese compared to pyrometallurgy, because these elements remain in the aqueous solution rather than being trapped in slag. Controlling the pH and redox potential is essential for maximizing the dissolution rate and minimizing the co-dissolution of impurities like iron and aluminum.
The dissolution of the cathode material, for example, lithium cobalt oxide, requires a reducing agent because the transition metals are typically in a high oxidation state, such as cobalt 3+. Sulfuric acid alone is insufficient to dissolve cobalt 3+ efficiently. Common reducing agents include hydrogen peroxide or sodium sulfite. Hydrogen peroxide acts as a strong oxidant, but also as a reductant in acidic media, reducing cobalt 3+ to the more soluble cobalt 2+. The reaction yields soluble metal sulfates and water. The use of hydrochloric acid is sometimes preferred because the chloride ion itself can act as a reducing agent, forming chlorine gas, although this requires careful off-gas management due to toxicity. Optimizing the acid concentration and temperature minimizes the leaching time and energy input. After leaching, the resulting pregnant leach solution contains a mixture of lithium, cobalt, nickel, and manganese ions. Selective separation is achieved primarily through solvent extraction or precipitation. Solvent extraction utilizes an organic phase containing specific chelating agents or extractants that selectively bind to target metal ions. For instance, Cyanex 272 is commonly used to separate nickel and cobalt from manganese. The metal ions are transferred from the aqueous phase to the organic phase, leaving other metals behind. Subsequent stripping using a strong acid recovers the purified metal salt. Alternatively, controlled pH adjustment allows for sequential precipitation, where metals precipitate as hydroxides or carbonates based on their solubility product constants.
Recovering lithium presents a unique challenge due to its high solubility and low concentration relative to the transition metals. Lithium remains in the final raffinate after the separation of cobalt, nickel, and manganese. The primary method for recovery involves concentrating the solution, often through evaporation, followed by precipitation. Lithium is typically precipitated as lithium carbonate or lithium phosphate. Precipitation as lithium carbonate requires the addition of sodium carbonate and careful control of temperature, usually above 80 degrees Celsius, to maximize yield. Achieving battery-grade purity, typically 99.5% or higher, often necessitates further purification steps, such as ion exchange, to remove residual sodium or calcium contaminants. Direct recycling bypasses the destructive chemical steps of hydrometallurgy and pyrometallurgy. The goal is to preserve the valuable crystal structure of the cathode material. This method involves physical separation, followed by a process called cathode healing or relithiation. The spent cathode material is treated with a lithium source, such as lithium hydroxide, and subjected to high-temperature annealing, typically between 800 and 1,000 degrees Celsius. This process repairs structural damage and restores the stoichiometric lithium content lost during cycling. Direct recycling significantly reduces energy consumption and chemical waste compared to traditional methods. However, it requires precise sorting of end-of-life batteries by cathode chemistry, as mixing different chemistries compromises the regeneration process. The environmental footprint of recycling is measured by energy consumption and the management of waste streams. Hydrometallurgy generates spent solvents and wastewater containing residual salts, requiring stringent treatment before discharge. Pyrometallurgy produces large volumes of slag, which must be safely landfilled or utilized in construction materials. Economic viability is driven by the market price of cobalt and nickel, but increasingly by the value of recovered lithium. The shift towards high-nickel, low-cobalt chemistries, like NMC811 and NCA, necessitates optimizing processes for nickel and lithium recovery. Environmental engineering focuses on closed-loop systems, minimizing reagent consumption and maximizing water reuse to ensure the sustainability of the battery supply chain.